All right, so any questions from yesterday? We were just kind of getting started, and I did an overview of kind of what the course includes. All right, so I wanted to mention the Engineering Computer Science Club meets here Fridays, 12 o'clock. If you haven't been to the club meetings before, I highly recommend at least checking them out. It's a group of students who just get together once a week and talk about or do whatever. If you're interested in working with people on projects or just sharing interesting ideas, it's a good place to do it. Sometimes they organize trips. Sometimes there's talks that are given. We had someone come in last year and talk about their work on building a space elevator. So they're with a company up north that's actually trying to design an elevator that goes from here up into space as an alternative to launching things with rockets. And some people actually ended up doing some work with this company as a result. So it's a cool opportunity for networking. It's a cool opportunity for just sort of listening to other people's ideas, sharing your ideas, and so on. Definitely come check it out if you're interested. So I want to start talking about set theory. This is our first topic for the course. And we said yesterday that a set is just a collection of things. It's an unordered collection of things. So a set is an unordered collection of objects. Sounds more scientific than things. So, for example, those are sets. This is also a set. It happens to be a collection of no objects, but it's called the empty set. But it's still a set, a collection of zero objects. And sometimes we just use this symbol, 0 with a slash through it, to mean the empty set. A set can also consist of just one thing, and we call that a singleton set. So this is a set consisting of no objects. A singleton set is a set containing just one object. And we can talk about membership in a set. For example, A is a member of this set. B is also a member of that set. X is not a member of that set. So to be a member of a set means you're one of the objects in that set. And we have a shorthand for that. Which is this epsilon symbol. And when you think of that as saying A is a member of that set, or A is contained in that set. And if something is not contained in that set, we can put a slash through it and say X is not a member of that set. And sets can be pretty much anything. A set of integers, a set of odd integers, a set of prime numbers, the set of rational numbers, the set of irrational numbers, a set of animals you can find at the Oregon Zoo, a set of foods you can buy on campus.
Do we like tables? Kind of?
Kind of, except tables are usually ordered. And these are really unordered. So this is exactly the same thing as this. If that makes sense.
Yeah.
Okay. We'll talk about how these relate to certain kinds of tables, though, and that may clarify it. So sets can be anything. If the set only has a few elements, we can write it by just listing all the elements in the set. If it had many elements, we'll sometimes use shorthands like S equals. And most of us would interpret this as saying that S contains 1, 2, 3, but also 4, 5, 6, 7, 8, 9, all the way up to and including 98, 99, and 100. But if you don't want to write all 100 numbers, you can use a shorthand like this. And so this set contains the first 100 positive integers. Or we could write something like which implies that it includes 1, 2, 3, but it keeps going, so it's all positive integers. And these aren't really rigorously defined, they're kind of based on our understanding that 1, 2, 3 means a set of sequential integers. But if we meant something more subtle, like would you think that 9 is a member of that set?
Yes, but I have a feeling you're wrong.
But you might be wrong because I might have meant prime numbers, 3, 5, 7, 11, 13, or I might have meant odd numbers. So this can be ambiguous. So we want a more precise mathematical looking way to specify sets, and we have a number of options. So for example, I could say P equals the set of all prime numbers. But that's too much English. Yeah?
Wouldn't a set have a finite number of numbers?
No, sets can be infinite.
Can be infinite?
Yeah, so the set of all integers is a set. So we could just use words if we know how to describe what we're interested in. If we wanted the set of even numbers bigger than 0, again, that might be obvious, or that could be something different. So here's a more precise way to define this. I could say E is the set of all 2n, and this colon you can read as such that. So this set is a set of all 2 times n, such that, or where n is an integer bigger than or equal to 1. So if n is 1, this is 2. If n is 2, this is 4. If n is 3, this is 6. If n is 1,000,000, this is 2,000,000. And our set is the collection of all things which are 2 times n, where n is some integer bigger than 1. So that's a way to define the set of even numbers bigger than 0. What set would this define? Set of all 2n plus 1, such that n is bigger than or equal to 1.
Odd numbers.
Say again?
Odd numbers above 1.
Odd numbers above 1. And if you want to see that, just start plugging in values of n and look for a pattern. If n is 1, this will be 3. If n is 2, this will be 2 times 2 is 4, plus 1 is 5. If n is 3, it'll be 6 plus 1 is 7. And you'll end up with all the odd numbers bigger than 1. If I wanted odd numbers that included 1, I have a few options. One option would be to let n be bigger than or equal to 0. Because now if n is 0, then this would be 2 times 0 plus 1. That would include 1. Or I could do 2n minus 1. Because now if n is 1, this is 2 minus 1 is 1. If n is 2, it's 4 minus 1 is 3, and so on. So we can extend that. And there's no rigorous, strict way to say, how do I go from a set to a description like this? It's kind of a trial and error thing, and it's an experience thing. It's more straightforward to go from here to this than to go from here to this. If you're trying to define a set, you need to find some sort of way of expressing it. But if you're given an expression like this, you can just start writing the elements and see what the set is. So what about this set? Is there anything in that set?
No.
So that's an empty set. Because to be an element of that set, x, it has to be bigger than 0 and less than 0. And we know from our experience that there's nothing that's both bigger and less than 0. Set. It's a singleton set containing one element, which is the number 0. So we could write z equals this. But you don't want to get overly excited and write something like that, because that's wrong. This is saying z is the number 0. That's not true. But z is a set consisting of one element, which is 0. That's correct. So sets are different from numbers, even though they can contain numbers. And so we have some sets that we'll encounter again and again. This funny looking n is called a set of natural numbers. And this is integers bigger than or equal to 0. This funny looking z is a set of all integers. Funny looking q is a set of all rational numbers. So what's a rational number? It can be expressed as a ratio. Yes?
How do you write that z?
I do it as a z, and I just put an extra line here on this bar. If you use a good text processor, there's a built-in for it. So a rational number is a fraction. something divided by something, where each of those somethings is an integer. So I could also write this as the set of all P over Q, such that P is an integer. P is contained in the set of integers. Q is contained in the set of integers. And I need one more requirement. Q not equal to 0. So there's a nice mathematical looking definition of rational numbers.
Is that okay if we write that like dependent to Z, or we need to also show what is Z over there?
The funny looking Z will assume throughout this course means a set of integers.
No, I mean, like as an example, if any other thing, could a set be dependent on another set?
Absolutely, yeah. That could be some other set that you've defined somewhere else. It could be the set of happy integers. So Q is the set of rational numbers. Funny, R is a set of real numbers. What's an example of a non-rational number or an irrational number? Pi. You can't write pi as a fraction. You can approximate it 22 over 7, but you can't write it exactly. What about square root of 2? You ever play with that?
It's 1.22 some.
Yeah, 1.414 something, something, something. And you can approximate it pretty easily with arbitrary accuracy, but you can't find an exact fraction that's equal to the square root of 2. And the Greeks discovered this, and it really teed them off. Pythagoras was, in some ways, a cult leader. He had a secret society of people who worshipped numbers, and they worshipped integers in particular. And they were fascinated with ratios of integers. And they felt that through whole numbers or fractions of whole numbers, they could represent anything. They were almost godlike to these people. And unfortunately, somebody discovered that a simple triangle with length 1 on each side, the length of this could not be written as a fraction. And they proved this. And this threw a big monkey wrench in their beliefs, because they thought that through whole numbers and ratios of whole numbers they could acquire all knowledge. And suddenly they realized they couldn't even represent the length of the simplest triangle with these fractions. And that was forbidden knowledge for a while. And one person actually tried to tell some people about this, and they took him out on a boat and they pushed him off. And he swam back to shore and he lived. But this was a real cloud on their parade. And this length turns out to be square root of 2. And it's a pretty straightforward proof that square root of 2 is not a rational number. And we'll look at that when we do proofs in number theory. But it's a really weird but kind of elegant proof. So there are things that are real numbers but that are not rational numbers, and pi is one of them, but even simple things like the square root of 2. And C is a set of complex numbers. So what's a complex number?
Rationals and irrationals?
Rationals and irrationals give you the reals.
Real and unreal.
Real and unreal.
Well, imaginary.
Imaginary, right. So you throw in the square root of -1, which we can call I here because we're not doing engineering. You throw this in with the reals and you get the complexes. So bigger and bigger and bigger sets. every integer is also rational and is also a real number and is also a complex number. It just happens to have nothing after the decimal point, no I component, and nothing on the denominator. So these sets get bigger and bigger and bigger. But there are numbers here that aren't in here, and so on. So those are some of the symbols that we'll use periodically. So how else can we define sets? So we can use what's called interval notation. For example, we will sometimes want to use a set like the set of all x, coming from the real numbers, such that x is bigger than or equal to a, and x is less than or equal to b. So what does this set look like? What sorts of things are in there? A and B will definitely be in there because assuming that A is less than B and B is bigger than A. What about stuff in between A and B? So think of a number line. And let me go ahead and say A is less than B so we don't deal with weird edge cases. So on a number line, A is sitting to the left of B. So this set describes this point and everything in between. Okay, so it's an interval. It's an interval starting at A and ending at B and including the endpoints. And we have a shorthand for that, which is just A comma B inside square brackets. And we call this a closed interval. Now we could also have a set of numbers coming from the reals. Which are strictly greater than A and strictly less than B. How does that differ from our closed interval?
A and B are not included.
A and B are not included, but everything else is the same. So here's A, here's B, and typically this is drawn with a little circle around A and B to say those points aren't included in this line, but everything in between is. And we have a shorthand for that, which is A comma B with parentheses instead of brackets. And we call this an open interval. And we can combine these and do things like half open or half closed intervals. So this would include A but not B. This would not include A but would include B. And this is a pretty simple definition, but it's a really sophisticated concept. Because open and closed intervals are very different from each other. And let me show you one way in which they differ. What's the largest number in this set? An interval is a set, right? It's a collection of real numbers. What's the largest number in that set? What's the smallest number in that set?
1.
No problem. What's the largest number in this set?
There isn't one.
There isn't one. If you tell me it's 1.99, I'll find a number bigger. If you tell me any number that's in that set, I'll find a number bigger than that. That's a little weird, isn't it? Every number has some element that's bigger than it. Does that happen in real life? Does everybody in this room have someone who's older than them? No, I'm pretty sure I'm the oldest. Does everybody have someone who's younger than them?
Among the set of people in this room?
In this room, yeah. So with finite sets of numbers, there's always a biggest number. With an infinite set of numbers, sometimes there's a biggest number, sometimes there's not. And in the second example, there's no smallest number either. You can get smaller and smaller no matter which number you pick. And that's a little freaky. And we can actually derive calculus from these two notions. You can do something called point set topology. It's an abstract version of calculus. Calculus is like point set topology applied to real numbers. But we can do it more abstractly on general sets. And open and closed intervals, these get into notions of continuity and limit points. And you can sort of branch off from there. It's a wonderful field. All right, so other ways to define sets: interval notation, open, closed, or partially open, closed intervals. Equality of sets. So when we write A equals B, what do we mean by that precisely?
They each contain the same elements?
They each contain the same elements. So I'm going to write that as follows. X is contained in A if and only if X is contained in B for all possible objects X. So to say two sets are equal means that for any object I pick, member of set, not member of set, any object I can think of, it's contained in here if and only if it's contained in here. If and only if means if it's contained in here, it's contained in here, and if it's contained in B, it's contained in A. We'll use if and only if a lot. So we have an abbreviation IFF, that means if and only if. And we have an abbreviation, instead of saying for all X, I can use what's called a universal quantifier. It's an upside down A. It means for all. So this would be the more classic way of writing what we mean by A equals B. So clearly those two are equal. But these are not equal. Why? Those are equal. An element is in here if and only if it's also in here, even though I've written this with 3 elements. But why are these not equal to each other?
Because the one on the left does not have a 3.
The one on the left does not have a 3. So there is a particular x, 3, which is contained in here but not contained in here.
Okay. So it goes both ways.
So it goes both ways. It could be contained in here if it's contained in here. And that's not the case. This is a set of all x, which is an integer coming from z, whose square is equal to 5. So what does this set look like? Is that an integer? So is there anything in this set? This is empty. This is the set of all numbers q, which are bigger than 10 and are an even prime number. Are there any even prime numbers bigger than 10? If you have an even number bigger than 10, it's divisible by 2. It can't be prime. So this is the empty set. So this set and this set are equal to each other. Their descriptions are obviously very different from one another. But as a set equality, they're equal. Make sense? All right. How many people here know Venn diagrams? Ooh, Venn. It was one of Google's doodles within the past year. It was the birthday of Venn, I think. So a Venn diagram is a way to describe sets that may have some relationship with each other. So we can draw pictures to correspond with some of these concepts. So for example, this is called the universe. Put a tail on it. This is the set of every object that you're considering. And for this example, this is going to be the set of all foods, all things that you can eat, which I guess includes rocks and dirt, technically. Yeah. And I'm going to draw a set C, which is a set of all cookies. And theoretically, every cookie is a food. You can eat them. So I'm drawing this as something inside this larger object. And I'm going to draw some other set, H, H is a set of all foods that have chocolate. So candy bars and chocolate pudding and everything else is in this set H. And so outside here, we might have a member of this set, which is a salad. And over here, we might have a member of this set, which is a snickerdoodle. Anybody not know what snickerdoodles are? great
Snickers in
cookie.
it? Does that have Snickers in it?
No, it doesn't, which is really weird. But it has cream of tartar. It's one of the few cookies with cream of tartar. And foods with chocolate in them. Put M&Ms in there. If you're taking nutrition, don't show these to your teacher. And I've drawn these set representations so that they overlap. Why is that? Because there are things that are in both sets. For example, this might be a chocolate chip cookie. And it's both a cookie and a food with chocolate, and it's a food that you can eat. So as we start talking about subsets, intersections of sets, unions of sets, complements of sets, we'll come back to Venn diagrams as a visual way of describing some of these things that we're going to describe mathematically. Okay, so it's another tool for visualizing some of these notations that we're going to talk about. We have 10 minutes left though, so before we start talking about subsets and intersections and things like that, I want to back up a little and I wanted to toss something out for you to think about. And I mentioned yesterday that set theory can be done in two ways. There's naive set theory, and there's what's called axiomatic. Set theory. Axiomatic sounds more technical, right? Axioms, we talk about them in geometry or maybe some other math courses. Axiomatic set theory is very rigorous. We don't use words like things and objects. Naive set theory is what we're talking about, and it's what we'll talk about in this week's lectures. But I want to show you what can happen if you follow naive set theory and you don't go to the rigor of an axiomatic set theory. So let's continue thinking of sets as collections of objects. And sets can be a collection of anything. For example, this is also a set. This set contains three objects. First object is the number 1. The second object is the number 2. The third object is the set of prime numbers. Nothing wrong with that. And we might think that this has an infinite number of things in it because there's an infinite number of primes, but this set itself, S, has 3 elements. 1, 2, and a set. Now this element itself, the set of primes, that's an infinite set. Has an infinite number of prime numbers in it. But S itself, 3 members. But this can get us into trouble. Once we start having sets that contain other sets, we've got to be a little careful. So I want you to follow me on this thought experiment. So here's a definition. A set S is called self-consuming. If it's a member of itself. If it contains itself as one of its elements. And I don't have a self-consuming set example I can put on the board. Because, yeah, it would be a recursive example. Here's a set, it contains 2 elements. This does not happen to be one of the elements. Right? And if I wanted to include that, that's a perfectly fine set. But it's still not self-consuming because it would need this to be an element. And it's not. The only elements are 1, 2, and this set with 2 elements. This does not contain a set with 3 elements. So it's hard to come up with an example of self-consuming sets.
So does it exist?
I don't know, but that's okay. We're not going to need to know whether it exists or not. Because this is math, right? We can do what we want. It doesn't matter if it's absurd, as long as it's logical. So we have a definition that may never apply to any set. But if a set contains itself, we'll call it self-consuming. Okay, so I'm going to define a set W equals the set of all sets that are not self-consuming. And we know there's at least one element in this set because we said this is not self-consuming. It doesn't contain itself. So this would be contained in W, and the integers would be contained in W, and the primes, and the set of animals at the zoo. And there's a lot of things in W. It's a really big set. Maybe it contains all sets. I don't know. But this is our definition. If a set is not self-consuming, it's inside W. Clear on the definitions? So, question. Is W a self-consuming set? So we have 2 choices, yes or no. It's a simple yes-no proposition. So 2 possibilities. 1, suppose we say yes, W is self-consuming. What does that mean?
It means it contains itself.
It means W contains itself.
But W only holds sets that aren't self-consuming.
But W only holds sets that are not self-consuming. So W cannot be a member of itself. So this leads us to a contradiction. So the answer must have been no. W is not self-consuming, which means W is not contained in W. But if W is not self-consuming, it's a member of the set. But then W is contained in W, contradiction. So we're doomed either way. If this statement is true, we get a contradiction. If this statement is false, we get a contradiction. So is it true or false?
So is that a proof that it doesn't exist? Which is going to be true?
Possibly. But we don't know yet if W itself is self-consuming. If we could prove from this that there's no such thing as a self-consuming set, then we've got our answer. W is not self-consuming. But oops, we've got a contradiction. Anything that leads us to conclude that this is true or false forces us into a contradiction. The only conclusion is that we cannot determine whether this is true or false. It's undecidable. Or perhaps it's neither true nor false. Talk about raining on your parade. So this was Russell's paradox. I think it's 2 L's.
It is.
Thanks. And it comes out of the fact that we were too generous in our definition of what a set was. We let a set be anything. And down here, to say that it's all sets allows it to possibly include itself. And that's not kosher. So when you do axiomatic set theory, you have a more precise definition of these concepts, and you can avoid these sorts of paradoxes. But around the turn of the century, 1900s, people were thinking of sets as collections of objects. And you came up with this, and it's like, okay, we got to be a little more careful now. This, I think, is part of what launched Whitehead and Russell, perhaps, onto their Principia Mathematica, where they tried to make everything rigorous in mathematics, so that 300-some pages later, you can lay the foundation for 1 + 1 = 2. The bummer of it all came out in 1939 by a mathematician named Kurt Gödel, who presented a very small paper at a pretty obscure conference, and most of the attendees had already read this paper and said, that's cool. They didn't really understand what it was. A few people did, and they were horrified. Because what Gödel showed was that this doesn't just happen with set theory, this happens with arithmetic. This happens with all of mathematics. Any time that you define a system of axioms to develop something like arithmetic, you have two options. You build in contradictions, or you build in things that you cannot prove or disprove, things that are undecidable. And it's somehow systemic. It's somehow fundamental to any time we try to develop one of these axiomatic systems. And it's called Gödel's incompleteness theorem. And we'll talk about it later on in the course, and it ties into something called the halting problem, which is an application of this basic concept to computer science. And it's a proof that there's some programs you cannot write, programs that cannot exist, which should really annoy you. Don't tell me I can't write a program to do this. But there's ways to prove this to some degree. So that's your paradox for the week. Tomorrow we'll go back to closer to Earth, and we'll start looking at operations we can apply on sets, subsets, intersections, unions, complements, and we'll move from there into how this ties into digital logic. And then we'll go on to some other weird stuff at the end of the week. All right, so I'll see you tomorrow.
So this is somehow similar to how we use lots of rules, including prime numbers, large and finite.
Prime numbers, having an infinite number, is a fairly straightforward proof.
But then we're going to have like three choices, this, or this, or this. So
but that we can actually get to. We can actually get to a case where we say, okay, yes, this is true.
Okay.
And a lot of what we argue in this class is proof by contradiction. We assume something, we get to a contradiction, and then we say, okay, so our assumption must be wrong. So assume there's a finite number of primes, we can get a contradiction, so there must be an infinite number. But things like this, whichever way you make your original assumption, you get to a contradiction. That's where the problem is.
So this is not proving that there is a third answer for this question.
There kind of is. There's this notion of undecidability, which basically says you can't prove, you can't disprove. Or more precisely, whether you prove or disprove, you have to find a contradiction. Or